for my...
Meeting is being recorded.
So let's get some concepts first. I was talking about near Earth space and what does it mean. So near Earth space is actually this kind of combined region of magnetosphere and ionosphere. Magnetosphere is formed by the magnetic field of the Earth, which is this kind of dipole type of magnetic field, which is turned to a kind of completely different kind of cometary type shape because of the interaction with the incoming solar wind. Some solar wind is coming in from the sun, and these orange lines depict the path of the solar wind, and that pushes this magnetic field together at the day side and makes an elongated tail which extends far beyond the moon orbit. So this kind of magnetic bubble, which is the magnetosphere, it's not a sphere, but that's the traditional name. And then we have the ionosphere, which is much closer to the Earth, which is just part of the upper atmosphere, which has been charged by the effect of the solar extreme ultraviolet radiation, and also by precipitating particles. So this is a charge layer which was found by Marconi when he was making these kind of radio experiments from Europe to Americas, and the ionosphere reflected these radio waves so that they could be heard over the horizon. Now, the space weather is a concept that has been with us since about 20 years. And space weather means basically solar eruptions and their effects to the Earth in any possible way. Some of these greatest eruptions or forms of eruptions are listed here. On the left, there is a coronal mass ejection. So here is the sun, and these mass ejections are huge eruptions of material from the sun, which can come even down to the Earth and cause a lot of disturbances. The largest disturbances that we have come from such ejections. Then we have solar flares. That's a smaller scale phenomenon, but they are very intense radio emissions, solar X-ray emissions, and solar EUV, so extreme ultraviolet emissions. So they also they are so strong that they can, when they direct to the Earth, they also can have effects to the atmosphere and also the technological aspects like communication, etc. And then we have solar energetic particles. These are kind of the most energetic, the fastest particles that can come from the sun, and they also have their own effects to the Earth's atmosphere. Now, space climate, on the other hand, is the long-term evolution of the space weather effects in the sun and all space dominated by the sun. And the long-term means here quite a large, range of time scales from a few months to several millennia. Basically, the whole period after the Ice Age, which is called the Holocene, can now be studied with some kind of solar activity proxies, and we know something about this whole period. More data exists for the last 100 and 200 years, so the special focus now for space climate has been this few hundred-year time scale. So we are not talking about kind of hundreds of millions years, the time evolution of the kind of stellar evolution of the sun. So only this kind of more recent millennia and centennia. So why to study the sun? I think there are very tangible reasons for that. First of all, the sun forms the habitable climate on Earth, together with the greenhouse effect. We have these pleasant conditions, and of course, the sun is the energy source for most biosphere. The sun is also the source for most energy forms used by mankind. Basically, of course, the solar radiation, solar panels basically nowadays used frequently, but also stored solar energy like oil, coal, gas, peat, tree, and etc. And even the flow energy in most cases, like water power, wind power, which is now also very famous in Finland also, tides, etc. They come from basically from the effect of the sun and partly the Earth's rotation. So only the, let's say, the main important form of energy, the nuclear fission energy, or nuclear energy as we now call it, is related to other stars than the sun. It's basically material that has been made by extinct stars in the earlier history of the universe. Now, also there is an acute reason to study solar magnetic fields because of its variability. We now know that solar magnetic fields vary actually at all time scales from seconds to millennia, probably even longer. And these magnetic fields also they control most of the effects that the sun has. The magnetic fields control solar irradiance, and because the magnetic fields change, they also change the irradiance, and the irradiance changes cause obviously changes in global climate. And also the number and type of eruptions changes in time with respect to the evolution of these magnetic fields. Now, one very dramatic event happened, or has happened actually a couple of times in recent history. One of these events was taking place in 1967, when a very massive solar flare occurred and produced very strong radio wave emissions. And those radio waves actually caused the blocking of the ballistic missile early warning system, and that led to a military panic in the US and of course everywhere else as well, where it was felt. So this was a period of high tension Cold War just before the Israel-Arab War, and indeed this interference of this early warning system was interpreted as a hostile jamming by the Soviet Union, and this actually led to near retaliation by the US. So US aircraft was armed with nuclear weapons, missiles, and they were put already to ready to launch status. But luckily, of course, the final save came by the US Air Force space weather forecasters who were monitoring the sun and reporting that, as they said, half of the sun was exploding. And they could convince that, okay, this event was from the sun and not from the Soviets. But this was so dramatic that this increased this kind of space weather monitoring very, very intensely, and especially in military, but also later in civilian usage. Okay, what is solar magnetism? We know that, well, first of all, the kind of first signature that has been known about this are the sunspots. So sunspots are a very specific type of magnetic structures on the solar surface. They are dark areas, and the darkness is because indeed of these strong magnetic fields that we now know that is roughly 2,000 times stronger than we have on the Earth, the magnetic field intensity. However, these are typically quite small regions, so they form only a very small fraction of the total magnetic total area, or even the total magnetic field on the solar surface. Even though they are kind of the Rolls-Royce, the culprit of the magnetic field structure, so they still are quite a small number and do not even contribute very much to the overall magnetic field of the on the solar surface. But anyway, the sunspots actually they reflect this kind of intense flux tubes. They are kind of magnetic ropes which are formed below the solar surface, and these ropes occasionally come to the surface, and when they cross the surface, these ropes are continuous, long ropes. Those places where they cross the surface, a sunspot is formed. So a sunspot is kind of an artifact of these kind of flux ropes, which extend themselves above the surface, sometimes very far away from the surface even, and so they are related to this kind of long structures of magnetic flux tubes. And because this flux tube is long and continuous, typically the two regions, there are two regions where these flux tubes rises and descends. So there are typically two sunspots are formed from this rise of a flux tube. So in flux tube, the sunspots tend to occur in pairs, but the pairs have opposite magnetic polarity, because in one case they come up. This direction is upward. The magnetic polarity or direction is upward, and in the opposite sunspot it is down. Well, anyway, this is a structure, and we have been able to observe these sunspots with telescopes already from the 17th century, and a researcher called Rudolf Wolf started counting these sunspots in the 19th century and even accumulated this or collected this information from the early 18th century onwards, and formed this kind of Wolf sunspot number, which is here. It is a sum of sunspots, the number of sunspots S, and 10 times the number of groups which these sunspots form. So this is a kind of artificial numbering, but anyway, this has been used now almost 200 years, and it is known since 1700, and we know now that here we show this variation of sunspot, the number of sunspots. We know that the sunspot increase and decrease at the rate of about 10-11 years. This is the so-called solar cycle or Schwabe cycle. And Wolf started numbering them from cycle 0 here in 1750. Now we are in cycle 25. In addition to this cyclicity, we know that the height of these cycles has changed. And it is now understood that this change is about 100-year cyclicity we call Gleisberg cycle. This is another German researcher. And this Gleisberg cycle, this 100-year or centennial cycle has formed has made very high cycles in the mid-20th century. So this cycle number 19 here has been the highest cycle for the last 300 years, actually 400 years. And it is now called the modern maximum, or actually the whole increase and decrease of cycle heights to this maximum and back. It is the modern maximum. Now, these high cycles, the period of high cycles has now decreased or stopped actually since about 15 years now. This cycle 24 was much lower than these active cycles in the mid-20th century. Now the cycle 25 we are still riding here was a bit higher than 24, but not at the level of these high cycles earlier. So what will happen in the near future is interesting to be seen. My own prediction is that the next cycle will be again a little bit lower, not higher, but lower. But this cycle 26, but then 27 would be another high cycles probably of this, and then it would increase until another maximum with a very strong activity in cycle 28. But okay, that's my personal expectation. Unfortunately, I will not be able to verify myself or see it myself, but somebody else might see. Now, I would like to just mention that the sunspot numbers are still under revision. So it is not yet fully established in all details. And especially the earlier, the earlier we go, the more uncertain it is. And there is an international team which is working on this, expecting to finish the next version of the sunspot number in about 2 years. And even most importantly, they want to establish an error estimate for the sunspots. Now it has no error estimate, and any such number is unscientific. So we want to make sunspot numbers more scientific. Now, this Wolf number was starting in 1700, but some earlier measurements exist since the times of Galileo Galilei in early 17th century. And American researchers Hoyt and Shetton have collected this information about sunspot groupings or groups from 1710 onwards. And an interesting fact is that they also saw this cyclicity in the start of this series, but then sunspot numbers or groups almost completely vanished for 50 years, 60 years. And this was another feature which is very interesting, which is now called the Maunder minimum. So it is the British researcher Maunder. Actually, this period was found by a German, but the name is given to the British guy. Anyways, so this is another interesting observation. Now we can have additional information from some natural archives which have stored this kind of information of solar effects within themselves. Most valuable natural archives are tree rings and ice cores, and these both have been studied very much in detail, and with this information one has obtained some proxy values for sunspots in the early centuries and even millennia. This is for the last 1200 years. And now the most recent, the time of the sunspot number observation was here. And we saw this Maunder minimum period, which was low period of low sunspot activity in the 17th century here. Now, before that, we can see that, okay, there were some similar periods of very low solar activity. They are named by Spörer minimum and Wolfen minimum, so, and even Oort minimum here. So we have this kind of large variability in sunspot activity, and the last 100 years has been quite active. And even earlier, this is a period of 12,000 years, basically the whole period after the Ice Age. So the Ice Age melted some 12,000 years ago, and here we can see that the first numbers of solar activity, so first estimates of solar activity, showed very large fluctuations, but also very high activity periods. And you can see all these fluctuations going on, very many grand minima, and this kind of longer-term trends in this occurrence of these great grand minima and maxima. But anyway, so very large variability in solar activity during this whole measured time interval, and we can also see that our period seems to be a very not exceptional, but most likely quite rare still in its high activity. Right. Okay, as I said, sunspots are kind of a Rolls-Royce of solar magnetic elements. Now, there are many other weaker magnetic field elements, and the most important ones are probably called faculae. I will mention this because of its specific role for solar irradiance. So faculae are bright. Here you can see a picture with these faculae as these bright areas, and then these dark spots are actually the sunspots here. So you can see that these faculae very often are around the sunspots, but also much larger areas, and even without sunspots, they can exist. And they have reasonably strong magnetic fields, not in thousand, but several hundred of the magnetic unit Gauss. So something like maybe 10 times or 5 times weaker, but again, much larger areas. And actually, the whole surface of the sun is magnetic. Here we see again these faculae. They are also called plages, of if I'm talking faculae or plages, the same thing. So, but in addition, you can see that the whole surface here has these green and yellow dottings. So we have magnetic field all over the solar surface. And actually, the smaller elements form the largest fraction of the total magnetic flux on the solar surface, not the sunspots. But the sunspots have been known for 400 years, But these other elements have not been measured so long. The faculae have been measured actually for 100 years, surprisingly, but these weaker elements hardly 30, 40 years. So we don't actually know for sure how the solar magnetic field evolves in longer term. As I said, we know sunspots for 400 years, but these more important, maybe the more important elements, we don't know so well. Now a little bit of this fact or this mechanism that produces these magnetic fields in the sun. First of all, the sun itself is a very ordinary fellow in the zoo of stars. It's a very mid-size, mid-active, mid-long lifetime star. So an average fellow in every sense. Now it has a production of energy in the core by nuclear fusion that produces all the energy that it has and emits into the space. Around the core, we have so-called radiative zone, where the energy comes from the core in the forms of radiation, obviously. And then the final third of the radius is called the convection zone or convective layer, where the magnetic field is formed, only here. So here it is formed because the matter itself is moving here in the convection zone. It is convected upward, and then after emitting its radiation, it's cooling down and then convecting down. So this kind of up and down moving convective cells exist here under the surface up to the third of radii down. This convective motion is one motion which is needed for this dynamo action. The other motion is rotation, and not only regular rotation, but the rotation which is called differential. So all the layers differentially rotate at their own rates, and that is in the convection zone. The core and the radiative zone, they rotate rigidly. It's like a ball rotating rigidly, but this convective layer is rotating differentially. And because of that and this convective motion up and down, you form this kind of electromagnetic friction which forms this magnetic field. Well, I'm not going to this detail so much. I wanted to talk a little bit of the solar irradiance because of its importance, first of all, of course. Now, the total the solar irradiance must be measured outside the Earth's atmosphere, because the atmosphere obviously absorbs much of the solar irradiance, not at every wavelength, but quite large fraction. So satellites are needed to measure this total or spectral solar irradiance, and it has been done so since the end 1970s. So we have something like 45 years, maybe almost 50 years of measurements of the solar irradiance by satellites. Now, and this shows the zoo of satellites that have measured these total solar irradiance. obviously it is this is a partial problem because we don't have one single measurement. We have several satellites that have been measuring this TSI for partly for some longer, some shorter time, but none of them more than 20 years. And they have to be somehow combined, and that is a problem, has been a very big problem, not only for space physicists, but also probably for climate people as well, because the absolute measurements, as absolute level even, has been different in the different experiments. And of course, all these instruments degrade in time when they make these measurements. They are degrading because of the radiation they measure partly, and also by cosmic rays and some other reasons. And this has to be also accounted in order to get the reasonable estimate of the or in order to combine these measurements from the different instruments. And this has led to several different estimates of this. Basically, three competing proxies or estimates of this long-term TSI have been made. They all agree on the fact that this TSI is varying at 11 years solar sunspot cycle. This variation is not very large. It's about 1 per mil of the amplitude. Well, the amplitude is about 1 per mil of the total irradiance. But it's still there, and it's in phase with sunspots. So the more sunspots you have, the more solar is emitting irradiance. But there is these two or three different estimates disagree a little bit on the long-term variation or evolution. So this one, which is so-called PMOD composite, made in Switzerland, this estimates this minimum minimum time level almost at the same level, maybe a little bit decreasing in time. So from minimum to minimum, roughly the same. And another one, Acrim, which is an American product, shows quite variable level for the solar minimum times. And another one, which is a Belgian product, obviously shows again a little bit different because the level of the irradiance increases from minimum here to the more recent minimum. So there seems to be kind of increasing trend in the total solar irradiance. Now, I have to say that most people, most solar physicists tend to favor this one, but I'm not so sure which of them is correct. It's a very tedious work to make this estimate, but anyway, this finding that this TSI is varying with sunspot number is very counterintuitive because sunspots are dark, and dark matter on solar surface would mean, and actually means, that those areas emit less than the neighboring areas. So why is it that the sunspots seem to increase, or the TSI seems to increase when sunspots increase? It is because of these faculae. The faculae also, the number of faculae also increases with sunspots. And they are bright, so they increase the radiation. And even they increase more so that they overcompensate the reduction in radiation by the sunspots. So the facular brightness is indeed overcompensating the dimming due to sunspots. And this long-held in-phase relation of sunspots and radiation is completely serendipitous, and thanks to the faculae. So this is just showing that the irradiance has a complicated, at least 2 or 3 term effect. So this is also neglected. We don't know what these smaller features, how they behave, and what they contribute. This is also another problem. But at least we have 2 major contributions. One is dimming by sunspot, and the other one is brightening by faculae. Now, the variation of solar irradiance, as I said, in-phase radiation with sunspots, is concerning most of the spectrum. So here we have the wavelength, basically the solar spectrum, and over the whole of the many different wavelength regions, the visible light is roughly here. So this is the light that we see, and then here we have UV, so ultraviolet, the extreme ultraviolet, and etc., etc. So shorter wavelengths, and here we have infrared radiation, so infrared light, and then radio waves. All these kind of all these kind of wavelengths are produced in the sun, and you can see that the solar cycle variability is quite different. It is quite constant here in the visible, roughly this 1 per mil range, but in the EUV it is much larger, up to 10%. And another interesting point here is that while most of the spectrum is behaving in phase with activity, magnetic activity, here some fraction of the infrared is counter behaving. That is also another interesting feature of radiation. Now, obviously, this knowledge that we have from these solar magnetic elements, sunspots and faculae, they have been used to reconstruct the TSI backward in time. However, we can see here only a few of these reconstructions, and they also seem to differ quite a lot. We can just compare this orange line and the blue line. They have, of course, matching. They are made to match here during the last 40 years. But when we go back in time, they differ more and more. So we still do not know much about how the solar irradiance is actually behaving in earlier times, especially just 100 years ago, or even before that. So we still do not have much information about that. Now, we were talking about the solar surface only so far, but the magnetic field extends above the solar surface, and it makes these large loops of these flux robes into the space above the solar surface, and it forms a kind of near sun space, which is the coronal, which is the solar corona. And solar corona has been observed quite a long time ago, even registered measurements since the mid 19th century. Some paintings and drawings exist from eclipses. It's because it so happens that the moon is just proper to mask the solar disk and allow the outer layers of the solar atmosphere to be visible, even the chromosphere, which is the closest one, and of course this corona, which extends to several solar radii outward. Now here is one example of measurements or observation of solar eclipse in 1842, and it has a typical structure of this kind of back-to-back lighted structure, in addition to this kind of round surface or round area. So this is a typical streamer, which, as we say, streamer structure in the declining phase of the solar cycle, when the sunspots are decreasing. So this seems to be very typical, and these observations have been made from different periods of solar cycle, and this, for example, here is a typical situation of the solar maximum time, when we have these kind of lighted streamers almost anywhere outside the solar surface, and in between only some small regions of less light or lesser emission. So this is a maximum time coronal structure, and this is a minimum time. So we have basically these two streamers back to back, and in between large empty or nearly empty areas and these are around the solar poles. So this is a minimum time configuration. It's a very different structure in different phases of the solar cycle, and this is an interesting observation that has been known obviously for already hundreds of years, perhaps even much older, because I would speculate that even the old Egyptians have known this variation, because they had the sun god called Ra, and they painted these kind of situations of the wings of Ra in the minimum time, or perhaps I don't know what time it was, but or how the structure was then. But anyway, and this could be the maximum time of the Ra in a similar fashion as it is showing these lighted areas, lighted streamers in more versatile way than during minimum time. Well, that's a speculation, of course, but nice history. So the corona has the matter in the streamers, but also the so-called these empty regions also emit particles, which are called solar wind particles. Now, solar wind is a continuous stream from the sun of particles, basically protons and electrons, not very energetic, not extremely fast, but continuous. And then these eruptions occur occasionally and modify this structure of this background solar wind. The solar wind was first found from the cometary tails by Ludwig Biermann in 1950s, and he even estimated the speed of this solar wind, which would cause this other tail of the comet. So this is the main tail, which comes from which is curved and comes from the dust material released by this cometary core. But then we have this gas tail, which is pointing always directly away from the sun. It's not curved, and this can be separated or seen separately quite frequently, not always, but he did a marvelous prediction, and which was which was verified later by satellite observations of the solar wind. And now we know that there are basically two types of solar winds, faster and slower. And this faster comes from these basically these holes that are between the streamers, while the slow solar wind comes typically from the streamers. And this has also an important effect for the Earth, because these fast solar wind streams coming from these coronal holes, they form interaction regions with the slow wind, which can cause a lot of disturbances to the Earth's magnetic field. And they actually are responsible for most moderate and weak storms that we have in the magnetic field of the Earth at any times. Now, I don't think I have much time. How is it now with you? Did you finish your first class, and how much time do you allow me still?
How much time do you want to take? We can carry on for a few minutes if you want to carry on.
Well, I would rather like to hear your. Maybe I gave you a little bit some advertisement about what we have been doing for the last 10 years with my students, and this is about the particles bombing the atmosphere. So basically, these solar disturbances they cause or they produce electric currents and electric fields that accelerate particles. They create radiation belts, and these particles precipitate into the atmosphere. And we have been studying the climate and atmospheric effects of these energetic particles during the 10-15 years. And this has actually been very interesting to show that they have relevance for the winter climate at high latitudes, especially in the north. Less there where you are in the south, because your climatology is different, especially in the atmospheric mid layer called stratosphere. It's quite different because of the Antarctica, and while here in the north we don't have this kind of cold area which would keep the pole cold at all times. Instead, we have rather warm summer, but we have, of course, cold winter. Now, what is this climatic effects is related to the wind streams, which are called the polar vortex. These are very strong winds in the stratosphere and are partly also in the troposphere, which is the lower atmospheric layer. And this is the strongest wind structure on Earth. They can attain very fast winds, especially in the south, but also in the north. And they partly control the winter climate even on the ground. Here I show just what this form of this vortex is at 30 kilometers, 18, 6 kilometers, and 1 kilometer. So even here and even on the surface, you find this structure of this polar vortex structure, and because we have observed that particle precipitation into this upper atmosphere and into the stratosphere actually have an effect on the structure of this polar vortex. These changes are mediated into the winter atmosphere on the ground, even on the ground. So, so maybe I will just skip some of the details, but we have shown that this polar vortex is indeed partly controlled by the precipitation, and that is strongest indeed in the declining phase where the particles mostly occur. So this kind of relation has been found recently. It is it has not been included yet in the in any of these IPCC evaluations because of its novelty, and but it will eventually. Then I think I will come to the conclusion. Some take some messages here to you. I think solar magnetic fields are indeed important for humankind via solar eruptions, so the space weather, via the effects of to the irradiance. And I still want to emphasize that there are many open issues about this field of science. We don't know the long-term solar magnetic activity of these small elements. We know sunspot evolution for 400 years, but we know very little about these smaller magnetic elements. And even the solar dynamo is not yet well understood. It actually has been completely changed during the last 10 years. And there's hardly any way of forecasting. Actually, the solar dynamo says that it is impossible in principle to forecast solar activity beyond half solar cycle, so about 5 years. Now, there are also some efforts to bypass this constraint, but indeed this is not yet fixed, or it's uncertain. And still nowadays we have new phenomena. We have new atmospheric phenomena, and there are also new ways of long-term forecasting of solar activity, solar magnetic fields, and also their effects to the atmosphere and climate. So I thank you for your interest. Thank you very much.
We've got lots of questions. If the online people want to ask questions, put up their hand, put a comment in the chat. I've got quite a few. I don't know if there are any in the audience, but I'm going to ask you to ask your questions, and I'm going to repeat it so that we can hear it on my mic and it gets onto the recording. Can I just fire away maybe with one or two quick ones? In your graph that went back for the 12,000 years, there seemed to be quite a spike in that period of activity, in that period when the what's the name, the ice age ended. And we're going into something of quite a spike in the near future, it looks like. Now, if you've got climate denialists seeing this, are they going to say, you see, it's not CO2, it's the sun? Is there any correlation like that in these spikes relative to the Earth's temperature? Is there any science which shows that?
Yeah, there are lots of sorry. Yeah, there are lots of sporadic evidences where a long-term relation, in-phase relation of solar activity and some climatic parameter has existed. There are several such observations in earlier history, even in recent, let's say, few hundred years time scale, and the solar effects have been known long time already to affect the let's say ocean temperatures and some other parameters. Now, final word is yet to come, I think, about this, but even it is probably hard to combine the early observations of some ice debris or some particles that have been drifted with icebergs. I mean, this kind of phenomena that existed 10,000 years ago. Now with the current climate, and so it is, yeah.
Well, with
I
that Maunder minimum, for example, I mean, it is a known fact, isn't it, that there was a year or two of much cooler temperatures than normal during that period.
Yeah, that is correct. Of course, that also may not be global. It may be limited to the Euro-Atlantic region, but still it is kind of a semi-global phenomenon. And I think all these climatic issues, they are very difficult because of these regional effects are different. And so stronger solar activity and stronger radiation could cause different types of phenomena in different regions of the Earth. So I think that this is a very difficult question and very open. The temperature itself is not a very good parameter to measure this kind of long-term change, because temperature is not an extensive measure of heat. Yeah, I mean, if you take a parcel, a hot air, for example, you move it from equator to, let's say, to mid latitude, you have a small effect. If you move it to the pole, you get a large effect to the temperature. So this is not a one
It's
should
complex.
one should measure these changes in terms of energy, not with temperature.
Okay, so
That's right.
Peter Kutzer has typed a question on the chat. He says, how is ozone affected during magnetic storms, and particularly across the South Atlantic anomaly when energetic particles penetrate deep into the atmosphere?
Yeah, this is a good question. The ozone is reduced obviously by particle precipitation. Particle precipitation is now documented to be able to cause radicals like nitrogen radicals and hydrogen radicals, which are very harmful for ozone. And these the particle precipitation, for example, to high latitudes where I'm living here, and even to the South Atlantic anomaly region, by different particles, obviously by stronger particles. But anyway, so the particles indeed cause these kind of ozone harmful radicals, and this has been documented very clearly, even quantitatively. And now the question is how much this effect is reflected into the dynamics and chemistry. Chemistry is documented, but dynamics is still a little bit less well documented. It is very plausible that these ozone changes are mediated into the troposphere, so basically to the climate on ground. And we have also studied this question, and I think we have strong evidence that this change this chain of effects of particle precipitation to ozone and then to dynamics is existing and is producing change to the polar vortex. And this is also interesting that the polar vortex is basically very much in the same region. It exists in roughly the same region as the auroral oval, which is the main region of particle precipitation. So it's probably not a consequence, not a coincidence that this connection exists. I have less to say about the particle effects to the South Atlantic anomaly. They are mainly indeed due to these stronger particles and probably not as effective in their climatic effect as the auroral particles and the polar vortex effects. But anyway, yes, basically the same.
Can I ask a quick question on that image you had of the bright areas around the sunspots? What did you call them? Auricle?
Faculae.
So is that exaggerated in that image, or can we discern that in the telescope viewing the sun?
Yeah.
Right.
No, that
we
was
will see the brighter area around the dark sunspot.
Yeah, absolutely.
Okay. All right. Anybody from the audience like to give it a go? I'm sure you've got lots of questions. Go for it.
Sunspot like a cone or flat, like an arrow.
So the question is the sunspot like a hole, or is it a flat area, just with a different temperature?
Well, yeah. Well, this is good question. It's the sunspots are indeed actually that the solar surface is kind of descended on the area of sunspot, so it's lower. The surface is lower there.
It is.
Yeah, it is. It makes a hole. Yeah.
It's just being pushed around by the magnetic influence on the plasma.
Yeah, it is due to the strong magnetic field and actually the reduced temperature that makes it to be reduced lower. Yeah.
Okay. Good.
I've got a solar filter, my telescope.
Yes.
I have never noticed faculae around the sunspots, possibly because the filter wavelength for sunspots and faculae is different. Am I right in assuming that?
Okay, so one person in the audience says he can't see the bright areas around the sunspots. Is that because our filters on our telescopes are not good enough, or is it just a bit dimmer than, and we just don't look carefully enough?
Well, yeah, the contrast is smaller to the background. I mean, so the sunspots are very much darker than the surface. Faculae are not very much brighter. They are brighter, but not very much brighter than the surface, the average surface. So it's more difficult to find faculae from the, let's say, the average surface. But you should try harder. maybe it is still possible to find it, but yeah.
Now that we know about it, we will try much harder to see it properly.
Say it again.
But now that we know about it, we will try harder to see it when we look at it.
Yeah, sure.
So just a different question on a different angle again. The sun is losing a lot of mass every second. I can't remember the exact figures that I've seen somewhere, but I think it's like tons per second or something.
That is true.
Does anybody measure any difference in the size or diameter of the sun? Is that something which is measured, or is that effect as a total of the whole mass too small to make any difference to the size of the sun?
Yeah, this is also a good question. I was wondering myself some time ago about this loss of mass, but as it is quite surprising that the total all the particles, all the mass that has has been expelled from the sun during its whole history makes little effect to its current mass. Hardly 1%.
Okay. Amazing.
Yeah, so this just shows the large volume of the sun, I guess.
Yeah. Anybody else?
So,
Another one? Go ahead.
Obviously, if the sun is huge and the mass is the same amount that's lost when the sun is smaller, it will have a very different expansion contraction rate.
Relative.
And then another thing is the intensity from the what we call the edge of the sun. Is it like travel straight? So does it travel straight out of the sun, or does it shine out at every angle? The front part is bright, and the sides are. You can see the curvature by the shade, or the intensity of the light. I was just wondering what the intensity of the light was from the edge of the sun as compared to the center of the sun.
So I don't know if you heard the question. Is wants to know
Not well, no.
different intensity from the edge of the sun to the center, but I think it's just that the center is aimed directly at us. That's why it's brightest. So it radiates probably equally out from the center of the Earth, of the sun. It does it or not? But
Sorry, I missed the point. I couldn't hear it.
so sorry. He's
Can you
asking,
repeat?
is there less radiation? I think he's saying from the edge of the sun compared to the middle. So
Ah.
That we can see.
That we can see from here, from Earth.
You mean at the edge of the solar surface compared to the center?
I think the explanation from that is just that on the edge of the solar surface, what we see as the edge is actually pointing away from us. So it's just for that reason only. And his other question was, if the sun is losing all this mass and eventually does become a bit smaller and it loses the mass at the same rate, then the rate will be quite a lot higher relative to the latter sort of mass that's left behind of the sun.
Well,
but that you're speculating probably works over billions of years still, I think.
yeah, well, sorry, but what will happen is that even though the sun is losing some of very small amount of its mass, it will not get smaller. It will get actually larger, but that's for different reasons. So the stellar evolution of the sun is to increase the solar volume and also increase the irradiance a little bit. So this is what's going to happen in the long future.
So at a couple of 1,000 million years, the edge of the sun is going to reach the Earth.
Not so quickly.
I think it was a very, very interesting talk and an enormous amount of information. I have recorded it. Do you mind if I uploaded it to our Hermanus Astronomy YouTube channel?
Yeah, for you, of course, it's okay, and I would be, of course, happy if I would get a copy of that.
Yes, certainly. I'll send you the link. Yes.
Yes. Okay. And thank you for your very active audience and people. I hope the Finnish students were as active as you.
Yeah, we're a little bit too old to be students, I think, most of us.
Okay.
Thank you very much for the presentation. It is very well received. Thank you.
Okay. Thank you. Thank you very much. Bye-bye.
Bye-bye.